PostgreSQL just became obsolete for AI workloads, and Databricks knows something everyone else missed.
Obsolete, but half the industry runs Postgres for their AI pipelines. So we're breaking down Lakebase's architecture, the instant branching feature, and how it actually handles OLTP at scale.
By minute 4, you'll know if this kills your current stack. Let's get into it.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're diving into Databricks introduces Lakebase, a PostgreSQL database for AI workloads.
Stick around to the end for today's headlines. Let's dive right in.
So, Databricks just dropped something that's making waves in the database world. Lakebase, their new PostgreSQL-based operational database. And here's what's fascinating. This isn't just another managed Postgres service. They're claiming it's an entirely new category of database architecture.
Wait, hold on. Databricks, the analytics company? They're building operational databases now?
That's exactly the reaction I had. For years, Databricks has been the lakehouse company, combining data lakes and warehouses for analytics. But now they're jumping into OLTP territory, going head-to-head with traditional operational databases.
That seems ambitious. PostgreSQL has been around for, 30 years? It's battle-tested, reliable, runs pretty much everywhere. What's Databricks bringing to the table that makes them think they can compete?
So here's their pitch, and it's actually pretty compelling. They're saying traditional operational databases weren't designed for AI workloads. Every query competes for the same fixed CPU and memory, so one heavy query can bring down your entire application. Sound familiar?
Oh yeah, we've all been there. That one analytics query that someone runs on production and suddenly your API response times go through the roof.
Exactly. And Databricks is saying that's becoming a massive liability as applications get more AI-driven. Think about it. You've got agents querying your database constantly, real-time feature serving for ML models, vector searches for RAG applications. The old architecture just wasn't built for this.
So what's their solution? How are they solving this differently?
They're completely separating compute from storage, not just logically, but architecturally. The compute is what they call lightweight and ephemeral. It spins up on demand. The storage lives in their lakehouse format, which means your Spark jobs and analytics engines can query it directly without ETL.
Okay, that's interesting. So you're saying I could write to this database through a Postgres interface, but then immediately query that same data from Databricks SQL or run a Spark job on it?
Exactly. No data movement, no ETL pipelines, no waiting for batch jobs to sync your operational data to your analytics platform. It's all the same data, just accessed through different compute engines depending on what you need.
But wait, if the storage is in lake format, how do they maintain ACID properties? PostgreSQL users expect strong consistency, transactions, all that good stuff.
Great question. And that's where it gets technically interesting. They acquired this company called Neon that had already figured out how to separate Postgres compute from storage while maintaining full compatibility. Then they bought Mooncake to improve the lakehouse integration. So this isn't something they built from scratch in 6 months.
What about performance? I mean, if your compute and storage are separated, doesn't that add latency?
You'd think so, but they're claiming instant branching, point-in-time recovery, and the ability to scale compute independently. Imagine being able to instantly create a full copy of your production database for testing. Not a logical copy, but an actual branch that shares the same underlying storage.
Oh wow, that's like Git for databases.
That's exactly how they're positioning it. And here's what's really clever. Because the compute is ephemeral, you can spin up different compute instances for different workloads. Your API might use one compute instance, your analytics another, your AI training yet another, all hitting the same data without interfering with each other.
This sounds almost too good to be true. What's the catch?
Well, there are definitely trade-offs we need to dig into. For one, this is a completely new operational model. Your DBAs who've been managing Postgres for decades, they'll need to learn new patterns. Plus, we're talking about a proprietary platform here. You can't just download and run Lakebase on your own infrastructure. Coming up, we'll dig into exactly how they pulled this off technically, what the real-world performance looks like, and whether this architecture actually delivers on its promises. All right, let's get into the technical meat of how Lakebase actually works. The key innovation here is what they call the Lakebase architecture. And yes, that's lowercase l because they're positioning it as a category, not just a product name.
So walk me through this. When I connect to Lakebase with my Postgres client, what's actually happening under the hood?
So you connect to what looks and feels like Postgres 17. They support all the extensions you'd expect, including PG Vector for AI workloads. But instead of writing to traditional Postgres storage files, your data goes into their Delta Lake format on object storage.
Wait, object storage like S3? Isn't that going to be way slower than local SSDs?
That's where their architecture gets clever. They're not doing synchronous writes to S3 for every transaction. There's a multi-tier caching system. Hot data stays in memory and local storage on the compute nodes. As data ages or when you checkpoint, it gets pushed down to the lake storage.
So it's kind of like how Redis handles persistence. You get the speed of memory with eventual durability to disk.
Similar concept, but with full ACID guarantees. They're using write-ahead logging, just like traditional Postgres, but the logs themselves can be stored in the lake. This gives you point-in-time recovery going back, well, as far as you want to keep the logs.
Okay, but what about indexes? Secondary indexes are crucial for OLTP performance. How do those work when your data's in a columnar format designed for analytics?
Great question. From what they've disclosed, the compute layer maintains traditional B-tree and other index structures for hot data. But here's where it gets interesting. Because the storage is in Delta format, you also get the benefits of file-level statistics and data skipping for analytic queries.
Oh, so you get the best of both worlds, fast point lookups for transactional queries and efficient scanning for analytics.
In theory, yes. In practice, there are some caveats. They currently support up to 8 terabytes per instance, which is respectable but not massive by modern standards. And while they claim instant branching, creating a new branch still requires spinning up new compute resources, which takes time.
What about consistency across these different compute instances? If I have my API writing to one instance and my analytics reading from another, how do I ensure they see the same data?
They handle this through what they call unified access controls and snapshot isolation. Each compute instance can read from a consistent snapshot of the data. For real-time consistency, you'd need to ensure your readers and writers are using the same snapshot or waiting for transactions to be fully committed to the lake storage.
That sounds like it could introduce some complexity for applications that need strict read-after-write consistency.
Absolutely. And this is where platform engineers need to think carefully. The auto-scaling version, which is where all the new features are going, can scale to 0. That's great for cost optimization, but what happens to your connection pools when the database scales down? What's the cold start time when it scales back up?
Do we have any numbers on that?
Databricks hasn't published specific cold start times, but based on similar architectures, we're probably talking seconds, not milliseconds. Fine for development environments or bursty workloads, potentially problematic for always-on production systems.
And what about the ecosystem? One of Postgres's strengths is its massive extension ecosystem. Can I just install any extension I want?
That's another trade-off. They support major extensions like PG Vector, PostGIS for spatial data, and PG Stat statements for query analysis. But you can't just compile and install arbitrary extensions like you would with self-managed Postgres. It's a curated list, similar to what you get with RDS or Aurora.
Let's talk money. How does the pricing work?
They're using Databricks units, DBUs, based on capacity unit hours. The auto-scaling version charges you for what you use with configurable min-max bounds. Storage is billed separately. The challenge is that DBU pricing can be opaque. It varies by region and commitment level.
So it could get expensive if you're not careful about your auto-scaling settings.
Potentially, yes. And here's something interesting. Jeremy Daly called out in his newsletter that the real innovation isn't the separation of compute and storage. Aurora and others have done that. It's the direct integration with lakehouse storage formats. Your operational data immediately becomes available for analytics with no ETL delay.
That's huge for real-time ML features and analytics.
Exactly. Imagine training your models on the exact same data your application is using, with no ETL delay, or running complex analytics on your transactional data without impacting your application performance. Stick around. In our final segment, we'll give you the exact checklist for evaluating whether Lakebase makes sense for your use case and what you need to watch out for. All right, let's get practical. When should you actually consider Lakebase, and when should you stick with traditional Postgres or RDS?
Yeah, because this sounds cool, but I'm trying to figure out where it actually fits in my architecture.
So here's my framework. Lakebase makes the most sense when you have three characteristics. First, you need both transactional and analytical workloads on the same data. Second, you're already invested in the Databricks ecosystem. And third, you have AI or ML workloads that need real-time features.
That's pretty specific. What about traditional web applications?
For a standard web app with predictable traffic, probably overkill. You're adding complexity and potential vendor lock-in without getting much benefit. But if you're building something like a recommendation engine where you need to serve features in real time and retrain models frequently, that's where this architecture shines.
What about migrations? If I have an existing Postgres database, how hard is it to move?
Since it's Postgres compatible, your application code shouldn't need major changes, but you'll need to rethink your operational playbooks. Things like connection pooling, backup strategies, performance tuning, all of that works differently in this architecture. Don't underestimate the operational learning curve.
What should I watch out for?
First, cold starts. Test your application's behavior when the database scales to 0 and back up. Second, pricing predictability. Run proof of concepts with realistic workloads to understand your DBU consumption. Third, extension compatibility. Make sure all your required Postgres extensions are supported.
What about disaster recovery and compliance?
The point-in-time recovery is actually a strength. You can restore to any point within your retention window, but you need to understand where your data lives. It's in Databricks' infrastructure, so make sure that aligns with your compliance requirements. They have SOC 2, HIPAA, and other certifications, but you're ultimately trusting a vendor with your operational data.
This feels like part of a bigger trend, doesn't it? The boundaries between operational and analytical databases are blurring.
Absolutely. We're seeing this from multiple angles. Snowflake has Unistore for transactional workloads. MongoDB added analytical capabilities. Even Postgres itself is getting better at analytical queries with columnar storage extensions.
So where does this go? Are we heading toward one database to rule them all?
I don't think we'll see complete convergence. Physics still matters. You can't optimize equally for random writes and sequential reads. But we're definitely seeing more hybrid approaches. The key insight is that data gravity is real. Moving data between systems is expensive and slow, so vendors are trying to bring compute to the data rather than moving data to compute.
But doesn't that create a different problem? Now I need different skill sets to manage these hybrid systems.
That's the platform engineering challenge right there. We need to abstract away this complexity for our development teams. Whether it's Lakebase, Snowflake Unistore, or whatever comes next, our job is to provide simple, reliable data APIs while managing the complexity underneath.
So what's your prediction? Will Databricks succeed in the operational database market?
Here's my take. They don't need to dethrone Postgres. They just need to own the intersection of operational and analytical workloads for AI applications. That's a rapidly growing market, and they're well-positioned with their existing customer base and lakehouse infrastructure.
Any final advice for platform engineers evaluating this?
3 things. First, start with a proof of concept focused on a specific AI or analytics use case. Don't try to migrate everything. Second, measure not just performance, but operational complexity. Can your team manage this effectively? Third, have an exit strategy. Make sure you can export your data and migrate away if needed.
That's solid advice for any vendor-specific solution.
Exactly. The technology is impressive, but at the end of the day, it's about solving business problems reliably and maintainably. Lakebase represents a new approach to an old problem. How do we serve data efficiently for both applications and analytics? Whether it's the right solution depends entirely on your specific context.
This definitely gives me something to think about for our ML platform.
And that's really the key takeaway here. The lines between transactional and analytical databases are blurring because our applications are becoming more intelligent. As platform engineers, we need to evolve our architectures to support this new reality. Whether that's Lakebase, another hybrid solution, or carefully orchestrated separate systems, that's the decision we all need to make. Before we wrap up, let's catch up on this week's infrastructure news. There's a fascinating expansion happening in the observability space. Elastic Cloud Serverless has just doubled its region availability on Microsoft Azure. They're now live in 8 regions worldwide, which is huge for teams looking to reduce latency and meet data residency requirements.
That's significant timing. With more enterprises adopting multi-cloud strategies, having that regional flexibility is becoming table stakes. Which regions are we talking about?
According to their announcement on elastic.co, they've added Virginia, Singapore, Spain, and Frankfurt. This means teams can now deploy their security and observability workloads closer to their actual infrastructure.
Speaking of enterprise infrastructure, there's an interesting piece on Cloud Native Now about private Kubernetes enabling hybrid cloud strategies at scale. What's the main angle there?
It's all about control and portability. The article highlights how private Kubernetes is becoming the bridge for enterprises who need the flexibility of cloud, but can't give up the governance and security controls of on-premises infrastructure.
Makes sense, especially with regulatory requirements. Are they talking about any specific implementations?
They emphasize vendor independence as a key benefit, being able to move workloads between clouds without getting locked in. It's that classic platform engineering challenge of building abstractions that actually work.
And speaking of regional expansions, AWS just lit up Elemental Media Services in Malaysia.
Right. The Asia-Pacific Malaysia region now has access to AWS's full media services stack. This is huge for broadcasters and streaming platforms in Southeast Asia who've been dealing with latency issues routing through Singapore or Sydney.
Video workflows are so latency sensitive. Having local processing for transcoding and packaging could be a game changer for live events in that region.
Absolutely. Now, switching gears to something really interesting, AWS published a guide on running containerized hybrid nodes with Amazon EKS. Alex, this one caught my eye because it's using Tailscale for the networking layer.
Oh, that's clever. So they're essentially running EKS worker nodes as Docker containers.
Exactly. The AWS Containers blog walks through setting up these containerized nodes that can connect back to your EKS control plane from anywhere. It's perfect for edge computing scenarios or when you need Kubernetes workers in locations where traditional EC2 isn't an option.
That's a creative approach to hybrid infrastructure. And finally, OpenTelemetry.io released their 2025 year in review.
The numbers are impressive. They've seen massive growth in localization efforts. The site now supports multiple languages with contributions from a growing international community. It really shows how OpenTelemetry has become the global standard for observability.
It's not just about the code anymore. Having documentation and resources in multiple languages removes huge barriers to adoption, especially in regions where English isn't the primary language.
That wraps up today's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
And check out platformengineeringplaybook.com for more resources and guides. Until next time.